rid of the chlorine, so then the high levels of chlorine aren't going into the environment. And then after it leaves that, the water is discharged into a small stream. That's called the effluent. Some other spots, I guess, here on the plant is you have aerobic digesters. So that sludge that I said, it builds up in the clarifiers and also builds up in the aeration basin will go to the aerobic digesters, and that's where they hold the sludge before shipping it out. That's called wasting it. That's when you're getting rid of the sludge. We have a reactivated sludge plant, so that means that some of the sludge is then put back into the aeration tanks. And then we have an equalizing tank up top, number 7. That's not in use at all anymore, but when we used to get wastewater from the jail, it would have a lot of volatiles. So you'd have to first put it in the equalization tank, bubble out any of the extra chemicals that were coming into the plant before it could go through the rest of the process.
Alright, so now I'm going to talk about data collection and our sampling process. So before we started doing any updates or thinking about any updates, we wanted to first look at the historical data. And first thing we did was we got the flow data from the plant, which for 2 years, and it gave us all like the flow, hourly flow and monthly flow. And then the next thing we got was the DMR report, which would give us all different stuff. It would give us suspended solids, total phosphorus, total nitrate, all different stuff you need, wastewater characterization. And we also got was sludge hauling with the activates. So then for sampling, we want to get the data. So these are the 7 spots where we did, or where we sampled: the influent, aeration tanks, the clarifiers, and the contact tanks. And after we sampled 3 times in 6 weeks. So with these samples, we got we tested suspended solids, total phosphorus, and total nitrate. We also did a microbial analysis, which Glenn did, which told us the health after aeration.
So now I'd like to tell you about some of the problems that the plant is having and how we're proposing to fix these problems. First of all, the plant can see excess flows during like spring snowmelt and big storms, and these excess flows can compromise the treatment process. Next, and probably the biggest problem, is nutrients, phosphorus and nitrogen. Limits on these nutrients are now being proposed by the Chesapeake Bay Initiative because down in the Chesapeake Bay, they're having big problems with eutrophication, which are basically just algae blooms. And this plant was built before this was even cared about by wastewater people. So it doesn't take care of these nutrients at all. And then the plant also, as Glenn was saying, uses chlorine. There's a new incoming limit for chlorine, I believe this summer, of 0.2 milligrams per liter. This can be met with the current system, but it will be costly. But more importantly, with the chlorine system, it's hazardous to the operators and potentially to everybody on campus if something would go wrong. And then lastly, we're having a little bit of dissolved oxygen problems. The blowers and diffusers, if you don't know the diffusers, that's just a little nozzle that blows bubbles into the aeration basin. They're old, they're broken, they don't work very well, so they need replaced. So some of our solutions for this are to, for the flow, use that unused tank that Glenn was talking about, to pump water in there when flows are high and then slowly pump it back into the system as water levels go down. As far as phosphorus goes, we're still in the process of hashing out whether we're going to use a chemical or a biological removal process. For nitrogen, we're sure we're using a biological removal process. As far as the chlorine goes, we're going to replace it with UV lamps. They're very efficient, they work well, they're easy for the operator to use, and they're safe. Then lastly, the dissolved oxygen. as I said before, simply just replace the blowers and pH.
Alright, so our plans for this semester, take a few more samples. We have our basic data from last semester, but we just want to see how the snow melt affects our loads and hydraulics. A site analysis, so looking at the equalization tank, see if we can use that to kind of dampen the load when the snow melt is a little higher, as well as seeing the space for any new systems such as the UV light. Sizing each unit based on our data, so seeing if we're putting in a nitrogen or phosphorus removal, seeing how big of a unit we need based on our loads. We're going to use STOAT, which is a treatment software model, to see how effective the plant is currently and how our new design will hold up to that. And then a cost analysis based on the sizing and the units that we're proposing. Our final design on CAD, and then any adjustments.
Going as fast as you can. 20 minutes left. Remember to write down your questions.
We're the Cool Cleanup Crew. My name's Drew Holler, and this is John. Andy's not here today, and our project on mine drainage discharge from the Puritan acid mine drainage.
Okay, so a little project background. Dealing with AMD from the Puritan mine. It plugs into a trout run located in Portage, PA. We have previous data from 1997 to help us design this footage. This is where a trout run is, and this is where our project station is. About a 20-minute drive. So what's the problem here? The problem is the current limestone treatment design isn't actually working. It only handles up to 100 gallons per minute. After that, everything's bypassed straight into trout run, polluting it and killing any stream life. So right now we have these influent discharges before treatment, and after treatment we get something more like it's limestone. It's not sports. And then to get clean, basically out of limestone you get clean water with stuff like that. There's also a problem with leakage in the system. The mass balance indicates about 20 to 30% leakage going from the influent to the effluent. So this is our current system, and this is how it works basically. AMD comes from the Puritan mine, it was through treatment, it was through all these baffles, and then goes into trout run, treating it through limestone solution. This is a problem. It doesn't handle anything greater than 100 gallons per minute. After that, if it goes in trout run, once again, fooling it, kind of thing. So, current treatment system works with a series of baffles, which stimulate turbulent flow in the system to promote chemical reactions. So, the water will go over and under, and over and under again, and out from the system for a 24-hour retention time. This is all the data we got. We were basically given. As you can see, it was initially the concentrations were really high, and then they kind of just mellowed out. We believe that this happened because when the system was first put in, the water traveling through the mine gathered like a lot of metals through the pipage, basically. So what were we sampling? What were we doing? We're using Y-side, take temperature, pH, DL, specific conductivity, flow for a bucket test, some stuff. It's all total metals in alkalinity. following standard methods and hoc methods. So here's what we're sampling. In addition to influent or effluent, we're also taking samples upstream, downstream to represent how the system is doing before and after treatment. Measuring the same stuff basically, alkaline, and we also installed a weir to look at high flows that's going through the bypass, so we know like how much they're actually dealing with. So we got from that to that. But unfortunately, recently our weir gave out.
Yeah, it's flowing underneath.
Yeah. So we're gonna do a temporary fix with some sandbags to get to that after winter.
So this is the results that we have from the current system. This is upstream, influent, effluent, and downstream. As you can see, the influent obviously has more higher pH and more metal loads. But there's a slight change in the downstream. This was for the data that was given to us, but we expect for like whenever snowfall comes, a lot more water is flowing through the bypass, which really affects the trout run in those spring months. So the objective for our project is to make trout run a cool water fishery. So we want our alkalinity levels and pH to be within all these ranges, and our metal loads to be roughly under 1 milligram per liter, which is the recommended for cool water fisheries. Some constraints and criteria is we would like to have properly line this, the new system and treat greater range of flows, and we're also limited within 1.5 acres of, that's where the current system currently sits. Some criteria is we want some obviously low impact on the environment. We'd like to have a low amount of operation and management of the system, and like be able to use heavy machinery to place more or replace limestone. In the system for the future. We did a lab scale experiment with on-site limestone from the current system. So the advantage of using the current limestone is that it's already been weathered and it doesn't have a real fresh limestone surface, which will kind of throw your predictions off for designing for something that's going to be there for many years down the road. So this limestone's already been through the system. It has a used surface, and we did pretty much